Okay, so last time I gave you a bunch of definitions, and now I'm going to actually prove some results. So one thing to point out is that everybody tells me that Israelis are very shy. So if you feel like asking a question or something, please go ahead. You don't need to be afraid. So especially when I start talking about more technical things, don't hesitate to ask for clarifications. This is the first time that I've taught any of this material, so it needs to be debugged. Everyone knows this. This is common knowledge. Okay, so this time we're going to talk about impossibility and separation results. So an impossibility result, which we'll do, is something that says that if I have a task that is a problem, I'm going to show that it is impossible to solve that in a particular model of computation. No matter how clever you are, no matter how long your algorithm runs, you can't solve it. I'm also going to do an example of a separation result, which says that some tasks are inherently harder than others, in the sense that I can solve a task T, given I can solve T prime, but not vice versa, at least in some models. And again, I'm going to try to do this in as model independent a way as possible. So first thing I'm going to do is I'm going to talk about manifolds. So this is a simplicial complex. A simplicial complex is a manifold if every two n simplexes, if every n minus 1 simplex is contained in exactly two n simplexes. Yeah, is the maximal dimension of any simplex. So for now, all the complexes we talk about are pure in the sense that all of the maximal dimension simplexes have the same maximal dimension. Later on, we'll relax this. Now, this is a kind of a discrete analog of your continuous notion of a manifold, which says that something is locally, looks like Euclidean space. So here, this just says that this looks like a surface. It's a continuous but not smooth.
Can you ask me to be shy? So can you repeat the definition?
So the technical definition is that you take every n minus 1 simplex, that is, you drop down one dimension, is a face of exactly two n simplexes, the top dimension. So informally, it means it looks like a surface in some dimension. Well, you could have three triangles that come together here, for example. So you could have, most simplicial complexes are kind of ugly. They have all kinds of things coming together. But these are relatively well behaved. And so we can extend this to say a manifold with boundary is just like a manifold, except we're allowed to have a boundary. And it says that every n minus 1 simplex is a face of either two simplexes here in the interior, or the face of exactly one on the boundary. So again, this is analogous to any continuous notions of manifold with boundary you may have seen in other contexts. But this is all discrete. And we'll misuse notation, and we'll use, this is what we call the boundary, which is the subcomplex consisting of all the n minus 1 simplexes that are a face of exactly one n simplex. So here, for example, this is a manifold with boundary. The hollow triangle is the boundary of this complex. So why are we looking at manifolds? Well, mostly because manifolds have nice combinatorial properties. Some things that we'll prove that will be a lot of work in the general case are relatively easy for manifolds. There are also lots of useful theorems that other people have proved. So one thing that's nice about this area is that you can borrow theorems from other people, and you don't have to prove them all yourself. The one thing that we'll see is that a lot of natural models of computation, the complexes associated with it are not manifolds. So later on, we're going to have to look at more general cases, but we're going to start looking at manifolds because they're easier than the general case. And the principles that we see working on manifolds, we'll be able to apply them later to the more general case. But this is a nice introduction to the kind of reasoning that we want to do in this area. So I'm going to start out with an example of a model of computation where all of the protocol complexes are actually manifolds. And this might look a little bit artificial, but in fact it's not quite as artificial as it seems. So we'll look at immediate snapshot executions. It's a restricted form of asynchronous read-write memory. So the processes share a memory. You can read and write locations. There's no bound on relative speeds. This has the nice property that all the protocol complexes that you get in this model are manifolds. So we can apply manifold theorems to them. And in fact, even though this looks kind of artificial, we can show that this is equivalent to regular read-write memory by showing that one can simulate the other. But we're not going to do that yet, or maybe ever, depending on how much time we have. But there are published results showing that these are actually equivalent. But for now, we'll just treat it as a particular model of computation. We don't care that that it's equivalent. So two things processes can do is they can write to memory. Here, each process up here has a slot in memory, and here the red process is writing a value 1 in place of a 0. And the other thing we can do is you can take a snapshot. That is, each process can instantaneously read the entire contents of the memory. Now, there are ways of writing snapshot algorithms that assume that you can only read one location at a time, and that still allow you to do snapshots. Again, we don't particularly care about this because we're going to take this just as the model. But in fact, that's part of the argument why this is equivalent to regular read-write. So immediate snapshot execution, we do the following. We repeatedly pick a set of processes. Imagine you're the scheduler. And I say you, and you can run. And then what they do is they all read together. They all instantaneously take a snapshot of the memory at the same time. Then they all, this should be write. That's a typo. Each one writes its state to a location in memory. And then they take a snapshot together. So they all write together and they take a snapshot together. So you can see the scheduler is fairly constrained here.
But they write to the same place?
No, they write to different places. So yeah. So imagine that each one has its own location in memory, and what I do is I keep writing my entire state to this memory. So we unbounded storage and so on. Since we're mostly interested in lower bounds, we don't care about resources. Okay, and then after we've done that, after they all write together and then they snapshot together, we pick another disjoint set and we do it again until everybody has had a chance to read. So everybody moves once. But the adversary can choose the order in which different sets run and what the sets are. And then we can do multiple rounds and do it again if we like.
And then the processes in the second side, they can write where the processes in the first?
Each one writes to their own. So if I write my value in the first round, and then you go in the second round, when you take your snapshot, you'll see mine, and you might write that out.
You can write in the same place.
You can write whatever your current state is.
It's a single writer model.
Yeah.
Okay, so what?
Each location belongs to a different process.
Yeah. Okay, so here is an example of a immediate snapshot execution. So I'm going to, so time runs from top to bottom. Each column represents the behavior of a process. So here, process P it writes its value and then takes a snapshot. Then when it's finished, the next process does a write and a snapshot, and so on. So this is an example of an execution where the sets are singleton sets, where each process runs by itself. And at the end of this, each process has a view of what happened. So here, P went first, it takes a write, takes a snapshot. Nobody else has written anything, so it sees only itself. Here, Q does a write and takes a snapshot, and it sees both P and Q, so its view is P and Q. And then, of course, R, which comes last, sees everyone. So this is one possible execution in this model. Now we're going to play some games with this and move things around and see what happens.
You said it's equivalent, this is
Yeah. It's a non-trivial argument. Basically, you show a simulation each way. So I would need to show you a regular read-write algorithm where I can simulate this, and it's like order n squared, reads and writes, things like that. So, but we don't need. I'm telling you this so you take it more seriously, but we don't need to know this, for the mathematical properties that we're interested in.
Okay, and I would like to know
Okay, okay. No, I can talk about it later, or we can talk about it afterwards.
But for purposes of lower bounds and such, you don't need to see equivalence.
Yeah.
To show equivalence, because you could just say these are the executions that I look at for the lower bound.
Yeah. So an adversary could say, I'm only going to run regular read-write executions that look like this, if you have a lower bound. So if I can prevent you from solving a problem in this model, then I can prevent you from solving the problem in any model that gives you strictly more executions. So now what I'm going to do is I'm going to take this and I'm going to move these steps up here and say, well, what happens to the views? Well, what happens is that by taking the last process to run and moving it one round earlier, exactly one view gets changed. So if you think of this as a simplex, we moved from one simplex to another, where two simplex to another two simplex that share an edge, because these two other values remain unchanged. The next thing I'm going to do is I'm going to take the set of processes that write last, and I'm going to move them up and say, well, whose view changes? Well, that changes the view of P. So by doing these little bits of adjustment, I'm changing one view at a time. So this is kind of suggestive of a manifold, because what I'm doing is I'm sort of moving around the manifold, changing one vertex at a time, and leaving all the rest unchanged. Now, if you take all of these views and say, well, each possible view is a simplex, labeled with the view and the process ID, and you write them all down on a piece of paper, you end up with this complex here. So this is what all of the possible immediate snapshot executions look like. So we have up here, I'm going to eat the color of a vertex is the process ID. So this is what the red process, and what did it see? What saw itself? And why is this? Well, because it ran by itself. It took a snapshot, nothing else happened, so the white equivalent question marks and the red means it saw red's value. Oops, did I miss something? Then down here, for example, this is a solo execution by green and yellow. So here yellow goes by itself, here yellow and green go together and they see one another, and then these are kind of the intermediate things where they're just slightly off. So if we take the executions that I showed you before, the first execution I showed you where P goes, then Q goes, and R goes corresponds to this triangle here. And you can sit down with a pen and a piece of paper and work this out. The next one that I showed you where P goes by itself, that's this vertex here, but Q and R go together, that's this edge here, is this triangle here. Then the last one that I showed you is this central triangle where all three of them run together. And notice that as I make these minor adjustments to the schedule, it changed one view. Well, that's the equivalent of saying I went from this triangle and I flipped it over to here, because the red and yellow views remained unchanged, but green changed. And then I flipped it again, leaving green and yellow unchanged, but changing the view of red. And if you fill in all the details, this is what you get. And so we'll call this a standard chromatic subdivision. Now notice I'm cheating a little bit here because I'm going to prove that this is a manifold. I'm not going to prove this is a subdivision. So I'm not going to prove to you that this really is a single triangle chopped up into pieces. First, because we don't need it. Second, the proof is kind of tedious. And third, I haven't introduced the machinery that we would need in order to do such a proof. So all we care about is that this is a manifold. We don't yet care that this is actually a triangle that's chopped up into pieces. I haven't told you. So yeah, in fact, in the course notes, I realized that it talks about subdivisions without defining it because I moved the definition later. So that's one thing that we need to fix. Okay, so what I'm going to do now is I'm going to go back. So when you think about standard chromatic subdivision, you can think about this picture. But that's not a definition. So I'm going to give you a combinatorial definition of the, what a subdivision is. And if we wanted to prove that this was actually a subdivision, we would work with that. But I'm going to give you a purely combinatorial definition of how this complex looks. So the first thing is, well, imagine that we have a single input simplex sigma. You know, we use the Greek letters for simplexes. And the protocol complex for one round of immediate snapshot is, we'll write it like this, immediate snapshot of a sigma. And that's that subdivided triangle I showed you before. This is the same thing as the standard chromatic subdivision. And each vertex is labeled with a process ID, that is, whose view is this of the computation, and is labeled with a face of the input simplex sigma, which is which inputs did it see. So if you think of the input simplex as being the tuple of all the input values, then at the time I took my snapshot, I saw some subset of them. Which ones are they? Well, that's what's given by this face of the input simplex. So each vertex is labeled with a process ID and a face of the input simplex. Now, the fact that this is immediate snapshot means that it has even more structure. So the first thing is that each process, remember, they writes first, and then it takes a snapshot. So that means that its own write must appear in its own view. So we'll write that by saying that each process PI has a vertex in its view. So whatever face of the input simplex it saw its own input. And so we use IDs here to represent the set of process IDs that appear. So what you do is everybody starts out with an input, and you write your input, and then you take a snapshot of the whole thing. So what you see is a subset of the inputs, which is you can think of as a face of the input complex. And so because I write first and then I snapshot, I'm guaranteed to see my own vertex in the view. And so that says that one condition is that my view has to contain my own input. And
you don't care what I write, just PI is in the view. I can write different things.
yeah, typically you assume that you have some input, which is maybe could be only your own ID or could be anything you like, and you write.
You write that and never write any other.
You write that, take a snapshot, and that's it for that round. And then later on, we'll talk about doing this for multiple rounds. But right now, we're only worrying about the one round execution. So all you do is you take your input, you write it, and you read. And then your final state is what you saw. Okay, the next thing is that snapshots are ordered. So that is that when you take a snapshot, it's instantaneous. So formally, what that says is that the snapshot for I and the snapshot for J, they could be the same, or one could be strictly contained in the other. But it's not the case that your snapshots are incomparable to each other, that I saw something you didn't and vice versa, because snapshots are instantaneous. It says that I just atomically read everything. And if you have two processes that both atomically read something, then one of them has to see at least as much as the others. So that's all that that says. So the next one says that when I write, then I take a snapshot immediately afterwards. It's not the case that I write, a bunch of other things happen, and then I take a snapshot. So what that says is if PI's input appears in J's view, then what PI saw is possibly the same or possibly less than what J saw. So let's look at that in more detail. So if PJ saw PI write, then PJ's snapshot is not later than PI's. So that just says that immediately after you write, you take a snapshot. And so it turns out that these three conditions give you a complete combinatorial definition of the immediate snapshot complex. And the fact that this is also a subdivision is something else that we're not going to prove now. But what we will prove is that this defines a manifold in a way that we'll get to. So the theorem here says that if I have, so I've defined this for a single input simplex, and it's easy to generalize this to an entire input complex. In fact, we need that if we want to talk about multi-round protocols. And so the theorem that I want to prove says that if the input complex that I give you is a manifold, and I run one round of immediate snapshot, then the result is still a manifold. So if you start out with a manifold and you run in this immediate snapshot model, then you end up with a manifold. And by implication, if you run multiple rounds of this immediate snapshot protocol, no matter how long you run, it's still a manifold. So it says that manifolds are closed under this kind of operation. So in particular, a single simplex is a manifold. So if I take a single simplex, I run immediate snapshot, I get a manifold. If I run it again, I get a bigger manifold, and so on. And informally, what you get is you get a finer and finer subdivision. But again, I'm not going to prove that. I'm only going to prove that what you get is a manifold. And this will turn out to be useful because there are all kinds of, some impossibility results turn out to be easy when you're working on manifolds and more difficult in the general case. Okay, so what do we have to prove to show this is a manifold? Well, I want to take an n-1 simplex of this protocol complex, and I want to show that it's a face of exactly one or two n-simplexes of the subdivision, because that's the definition of a manifold with boundary. And so what I'm going to need to do is to take the combinatorial definition of the immediate snapshot protocol, show you that any n-1 simplex there is either a face of exactly one or two other simplexes, and then that's all we need. So one way to do this is say, okay, so I'm going to take this n-1 simplex, and then without loss of generality, what I'm going to do is I'm going to re-index the processes so that the views that they saw are increasing by inclusion. So one way to think of that is to say that this one ran first, then some set here ran first, then some set here ran next, and so on. And that just means that we don't have to have doubly nested indexes when we talk about things. And in particular, the view of the n-1st process is the view seen by the last process of this set to run. So that's the biggest view of all, because it came last. So it took a snapshot, and when it took a snapshot, everyone else who's listed here had already written, either at the same time or earlier in time. So another way to think of this is I want to count the ways if I take an n-1 simplex with the process IDs and views, these are the vertexes, and this is the simplex. How many ways can I add a final vertex with the missing process p sub n and its missing view sigma sub n? And what I hope to prove is that there's exactly one or two ways of doing this, given the definitions. Okay, so turns out there's three cases we need to worry about. So it could be that the last view here has dimension n-1 or dimension n. So it can't be any smaller than that, because all of the n-1 processes have already written by the time this guy runs. So he's got to see at least n-1 other values. Maybe it saw everyone. So either this was in the last group to run, or it was in the next to the last group to run.
So it's dimension n-1, but it sees it's n or n plus 1.
Yeah. What's confusing is the dimension is off by 1 from the number of processors. That's not my fault. But this says it saw n plus 1, all n plus 1, and this says it saw n, all but 1. Okay, if it saw an n minus 1 simplex, then we know that the input complex is a manifold. So that means that either that n minus 1 complex is an internal simplex, it's the face of 2 n simplexes in the input, or it's the face of 1, it's on the boundary. So that gives us 3 cases to worry about. And so what I'm going to do is I'm going to just do a case analysis and go through all these 3 cases and show you why things work out in each case.
If you were looking at just one input simplex, you would have here just a boundary.
Yeah.
You need the other case because it's possible, because you want to be ready for the
Inductive case, yeah.
Yeah.
Yeah, because I want to say if I have a single simplex, then you're right, then that other case wouldn't, one of those 3 cases wouldn't happen. But because I want to do this inductively and say you can run for multiple rounds and so on, then I need the input to be a manifold and not just a single simplex. Yeah.
Why did you mention the n? I mean, there are only n processes.
There's n plus 1 processes. So one thing that's the tradition in topology is that if you have a simplex with n plus 1 vertexes, that has dimension n.
Right, but here I see from 0 to n.
Because there's a missing process. So this has.
What was before, and now we are right.
So what I'm saying is I'm looking what happened to all but 1 process, and I'm going to fill in with a view of the missing process. And I want to show that there's exactly 1 or 2 possible missing views here. So P sub n is the mystery process. We have to figure out what it saw. Okay, so let's look at the first case. So here, this is, let's say that the last view was this boundary simplex of the input. So this big triangle is the input simplex, the small triangle is the protocol complex. And again, when I show you these proofs in these pictures, don't take the proofs literally. Sorry, don't take the pictures literally. These are there to illustrate the idea. And the argument itself is completely combinatorial. The pictures are, in fact, sometimes a little bit misleading because I'll draw a triangle where it's supposed to be an n-dimensional simplex and so on. So you have to be careful that you don't conclude from a picture something that I'm trying to prove otherwise. So this is the view seen by the last process of the n processes to run. And so the n minus 1 simplex could be this one, could be this one, could be this one. Well, say it's this one just to make the picture concrete. And what do I know? Well, there's exactly one simplex, because I assume that this is a boundary simplex, there's exactly one simplex of the input complex, sigma, that contains it. That's this big one here. So there's only one input n simplex that contains the input n minus 1 simplex that was the view of process sub n minus 1. And that's the case that we're analyzing. So this is the assumption, and then we'll work from that. But then, given our definition, there's exactly one n simplex of the subdivision that contains it, which is we take process P sub n and we throw in sigma. Because it must have seen, when it saw this, it didn't see, P sub n didn't see itself, so it must have seen itself when it took its view, because that's one of our combinatorial conditions. And the only possible simplex that could be is sigma, because that's the only one that contains this. So that says that if sigma sub n minus 1 is a boundary, then when we extend it to an n simplex in the protocol complex, it remains a boundary. So boundaries go to boundaries. Okay, case 2 is suppose that this is actually an internal n minus 1 simplex instead of a boundary. So suppose this is the last view seen by a process, is this edge here, which you can see is internal because it's the face of two big triangles. And again, the t sub n minus 1 that we're looking at could be any of these three, but we'll pick this one for pictures. Okay, now it turns out because this is a manifold by hypothesis, and this is an n minus 1 simplex, and it also by hypothesis it's an interior n minus 1 simplex, there are exactly two n simplexes, input n simplexes that contain it, sigma sub 0 and sigma sub 1. And so it turns out that there's exactly two ways we can extend this in a way that's consistent with our rules. We can take p sub n and sigma sub 0 and p sub n sigma sub 1. And by the same arguments I gave you before, it can't be smaller simplex, so it has to be this one. So what I've just shown you, and in the notes this is done in even more excruciating detail, that this edge here is a face of two n simplexes. Yeah?
What do you mean when you say it also before, that the input simplex contains this simplex? What do you mean by contain?
So is a face of. So this big triangle here is an input simplex. This blue line here, so I have two complexes superimposed on each other in this picture. So the input complex is this, consists of these two triangles, two big triangles. And then the protocol complex is all the little triangles. And again, I'm showing them here as one is a subdivision of the other, because they are, but we don't know that yet. But this blue edge here is an input simplex. So we're looking at the blue edge, ignore all the small triangles. So I'm saying by hypothesis, let's assume that the last thing that you saw was this edge here. That's contained in this big triangle and this big triangle, again by assumption.
But you have to prove for that it's a subdivision.
No, I'm not going to prove that it's a subdivision. I'm going to prove it's a manifold, which is a weaker. We don't need induction here. So all that I'm doing here is saying that if this last view, this edge here, is in between two input simplexes, it's a common face of two n simplexes, then given our rules for doing the protocol complex, it must be the case that I can construct two and only two simplexes that contain the n minus 1 simplex of the protocol complex.
Because the last process must see everyone and it has two possible inputs.
Yeah.
These are the two
Yeah,
ways to
exactly.
extend.
Yeah. So the missing process Pn either had this input or had that input. And when we append that view or that view, we get these two triangles here. So that's just part of the case analysis that says that if your interior n minus 1 simplexes go to interior n minus 1 simplexes. So the last case is suppose that the sigma Sn minus 1 is an n simplex. So suppose the last one the last process of this set that ran saw everything. And so that's the last possible case. So what that means is that, for example, the n minus 1 simplex we're looking at might be this one here. And the last process happened to see everything. So we're no longer, before we were on the boundary of this simplex, but now we're looking at an interior edge of the simplex. And so here, well, suppose that, so we want to know what did p sub n see? Well, first we ask who saw p sub n. So let's say that p sub k saw p sub n. And let's say, and that says that by our combinatorial rules for defining this thing, that sigma sub n must be a face of sigma sub k.
So you know the sub n minus 1 saw Pn because it's of dimension n.
Yes, yes. So we know that somebody saw
n
P sub n.
minus 1 is n minus 1, but maybe less than that.
Yeah, yeah. So somebody saw Pn. So what we're going to do is we're going to find the division between the processes that did and the processes that didn't. So let's say that K saw it, but K minus 1 didn't. Oh, the other thing we know is that P sub n, well, this should be K minus 1. So there's a typo here. That should be K minus 1. So we say K minus 1 didn't see, but K did. So that tells us something about when Pn was scheduled in the execution. There's a special case where everybody saw Pn. In that case, we'll say that sigma sub n minus 1 is the empty set. That's not going to be a problem. So P sub k minus 1 did not see Pn, P sub k did see Pn. And I'm going to argue that there are only two possible views, there are only two possible things that P sub k could have seen. Well, so what we know is that sigma sub n is either contained in or equal to sigma sub k, but we also know that sigma sub k is strictly contained in sigma sub n, because k minus 1 didn't see n, so it can't be contained in it. That's what it means to not see it. So we put these together. We have two choices. Either the inclusions are strict, or this inclusion is equality. Those are the only possibilities given our definition of how the thing is constructed, which is promising because we want to show that there are two possible views P sub n could have had. So if we show this graphically, then in this execution here, P sub k, that is the red process here, didn't see P sub n. And here, this process, this is P sub k, it did see Pn. So one possibility is P sub n was scheduled between P sub k minus 1 and pk, which would give you this vertex here. Or it ran in the same group as P sub k. So either k minus 1 ran, n ran, and k ran in three separate steps, or k minus 1 ran and n and k ran together. Those are the only possibilities. And so that means that there's only two possible ways of filling in views for P sub n. So once again, we've shown that this edge is a common face of exactly two n simplexes. So that says that that's a manifold, and that's all the possible cases. So that's a proof that well, if you look at the notes and ignore the typos, then it's a proof that this is in fact a simplex. But these are most of the details.
Can you
Yep.
argue in this case that from K on everybody sees everything, or like they're all lumped together?
Well, we only let, not necessarily, because k plus 1 may or may not have seen k. So from that point on, everyone saw P sub n. But whether they saw each other or not is yet to be determined. If this doesn't show up in the two-dimensional pictures, because the three of them have to be the only three things. But if this were higher dimensional, then there would be more possibilities there. Okay, so we can take this idea and just sort of generalize it and say, well,
You know that Pn has a view that contains everyone?
no, Pn does not necessarily have a view. In that last case, Pn does not necessarily have a view that contains everyone. Because when we take the n minus 1 simplex, we're arbitrarily excluding one process, and that process could have run early or could have run late. And so it's not the case that the missing process saw everything. In the earlier two cases, where we're looking at the boundary, that last P sub n did see everything. But in the third case, P sub n minus 1 saw everything.
Okay.
And so that means that P sub n could have seen anything in between.
Okay.
Because somebody's got to see everything. Who's ever in the last group has to see everything. But once P sub n minus 1 sees everything, then P sub n minus 1 is free to scheduled anywhere. Yeah, yeah. Okay, so let's generalize this and say, well, let's define, you can think of a protocol as being kind of an operator that takes an input complex and gives you back another bigger complex. And we'll get to this later on when we have a little bit more machinery. We'll talk about these things as operators with certain properties. But for right now, just think of this as something that carries a complex to another complex. So we'll say a protocol is a manifold protocol if it preserves the property of being a manifold. So if your input is a manifold, then so is your output. And then for technical reasons, we also wanted to preserve boundaries. So it says that you can think of the boundary of as being the place where only a subset of the processes run. So in a model that admits failures, what we're saying is that if you look at all the executions where some processes just never participate, then the result still makes sense. And we've seen one example of a manifold protocol, which is the immediate snapshot. That's sort of the most natural one. Later on in this lecture, I'm going to build a totally different looking manifold protocol, which will be somewhat more artificial in order to prove a point. But we can generalize and say that if it preserves manifolds and boundaries, then we'll call it a manifold protocol. So I promised you that manifold protocols would have nice kinds of properties. Oh, and the thing that matters from this definition is that it's closed under composition. So if I show you that, what I showed you was that if you have an input that's a manifold, you run one round of immediate snapshot, it's still a manifold, then you can run as many rounds of immediate snapshot as you want and it's still a manifold. And so that will be useful. So let me remind you about one of our favorite problems, which is a case set agreement. Here, everybody starts out with an input. Some of my slides are missing, yeah.
In the previous slide that you said about the boundary preservation.
Yes.
I think a boundary of a simplex is a lower dimension simplex that simply represents a subset of the states of the larger simplex.
Yes, yes.
So if you have, for example, a failed detector that if one process doesn't participate, then the other processes move to a different state. That means that they know that it failed. Then it isn't a manifold protocol because they move to a different state that they know that it failed instead of being in a substate of the states that could have been if everyone.
Not necessarily, because all we're saying is that that if you run the protocol on the boundary, that is the subset, then what you get is the same as running the protocol and then sort of throwing out information about the processes that ran. But all that says is, in some sense, is that if you look at the executions where only a subset run, or you start out with a subset and the others fail before taking any steps, and then you run the protocol, that's the same as looking at all the possible executions and then throwing out the ones where where the processes make any steps. So this property could still hold with failure detectors and the like, because the manifold, adding failure detectors changes the properties of the manifold protocol, but it would change it on both sides of the equation.
But if you have a failure detector, then when a process fails, you don't just get a subset of the state, but you get a new state.
Okay.
Because the others know that.
Yeah, yeah. No, I think in that case you would not have you're right, you would not have a manifold protocol because the executions where somebody failed is not the same as taking. So the thing is, it might or it might not be, because you might also have the property that if you look at all the possible executions and throw out the ones where the process takes steps, those are exactly the ones that do have failures and where the processes would act that way.
That's the normal.
Yeah. So it's not clear one way or the other. We're not going to talk about failure detectors, but that's an interesting possible direction for future research, in fact. There is one paper that talks about failure detectors with this kind of machinery, but it's an. Oh, yeah. Actually, no, I would love to see something like that. Okay, so I'm missing a couple of slides here, but basically case-state agreement, everybody starts out with some number of values. They agree on at most k of them. Everybody picks one value. The number of distinct values is less than k. So what I'm going to do now is talk about the connection between case-state agreement and a classical theory of combinatorial topology called Ashburner's lemma. Okay, here we are. They're out of order. So afterwards, you end up agreeing on at most k, where in this case, k is 2. Okay, and the theorem here is that no manifold protocol can solve any non-trivial form of set agreement. In particular, the immediate snapshot protocol can't solve it. And since the immediate snapshot protocol is a restriction of read-write memory, that means read-write memory can't solve this. And this is a, at this point you may be sick to death of seeing proofs of impossibility of case-state agreement, but this was once an open problem for a long time. Okay, so I'm going to start out with a notion that we'll call a Ashburner coloring. I'm going to give you an informal definition first and then a more formal definition. So I'm going to take informally, I'm going to take a triangle and chop it up into pieces, subdivide it, and tell you what Ashburner coloring is on this. Then I'm going to go over it and talk about Ashburner colorings on manifolds with boundaries with a somewhat more formal definition. But the informal definition, the intuition you get from the informal definition should be good enough to make your way through the rest of it. But for people who like things precise, we'll do it twice. So we have a subdivided triangle here. Each of the corners gets a distinct color. It's obvious what corner. Because I'm being informal, I can rely on your intuition to figure out what a corner is. Each of the edges, along here, take a color from their corners. So everything along here is either red or yellow. Everything along here is green or yellow. Everything here is a red or a green. I hope nobody is a red-green colorblind. Yeah. Oh, sorry. Actually, when I used to work for a company, I got into trouble once because I had a slide where all the distinctions were in red and green. And the diversity officer of the company took me aside afterwards and said, you can't do that. So and all the interior vertices have to take one of these 2 colors. Okay, so that's a Ashburner coloring. So what Ashburner's lemma says is that at least one n simplex has all the colors. So no matter what coloring you do, if you follow these rules, distinct colors on the corner, and then you choose colors from the boundary, then in fact there'll be an odd number of simplexes with all colors. And in fact, I'll give you a quick proof of this. Usually I won't try to prove all the classical theorems, but this one is so easy that I can't resist going over it. Also, the techniques will be useful later on. Okay, so now I'm going to roll back and tell you what Ashburner coloring is for a manifold with boundary. And this is intended to be a little bit as precise as you can be on a PowerPoint screen. So we're going to give you an inductive definition based on dimension. So a one-dimensional, any one-dimensional manifold with boundary looks like this. It's just that you take a line and you put vertices on it. The boundary consists of 2 vertices, and then there's a bunch of stuff in the middle. And so we put one color at one edge. We put one color, a different color at the other edge. And everything in the middle has one of those 2 colors. So that's Ashburner coloring for a one-dimensional manifold. The inductive definition says that we have an n-dimensional manifold that's colored with some set of process IDs, capital Pi.
And how do you decide whether the one-dimensional stuff? I mean, if it's a circle.
So a Ashburner coloring is any coloring where you have 2 different colors at the edges, and then the interior colors are chosen from one of those 2.
So you decide where the vertices are?
Yep, you pick any color you want, and Ashburner's lemma will say that you've got to have an odd number that has all of the colors.
Is a circle not
A circle, okay, so technically a circle is a manifold but it's not a manifold with boundary. So it's important that the boundaries here are going to be non-empty, because Ashburner's lemma does not hold for manifolds without boundaries.
But I mean, if it's a simplex, you know that you take the three vertices,
Mm-hmm.
two-dimensional simplex, and then color each one in one color. But if it's a manifold, how you decide which you color arbitrarily and which ones?
For the manifolds, for the one-dimensional manifold, I just told you what the color is, and now I'm going to tell you how it works for higher dimensional manifolds. It's an inductive definition.
Okay.
So the idea here is that, so I have an n manifold, and it's colored from some big set pi, which is going to be process IDs, but that doesn't matter here. And so I have to, if I take the boundary of the manifold, I can write it as the union of m sub I, where m sub I is a non-empty n-1 manifold with boundary, colored with pi except for I.
There may be more than one way to do this.
Oh yeah, there's lots of different, there may be lots of different ways to do this. I mean, in all the examples, there'll be only one way to do this decomposition, because the coloring will basically
If you
fix.
have coloring, there's only one way to
Yeah,
do
yeah.
this decomposition.
Yeah, and so the coloring just says that you have to be able to take the boundary, break it up in each of these pieces.
No, because if you have coloring, then you only have one to.
I beg your pardon?
If you have, say a triangle and this is red and these two are red, then you can put your vertex here or here, it will still be legal.
Yeah, I think there may be more than one way to do that coloring.
This is something else.
Yeah. Yeah, so if you give me a coloring, this is the test I apply to it, say, yes, this is a Ashburner coloring, or no, this is not a Ashburner coloring. And so the idea is I have to be able to decompose the boundary into a bunch of pieces. No. Doesn't, as long as they're pieces. Typically they're not disjoint, because they'll if you think of the triangle, the edges of the triangles meet. So these are typically not disjoint, in fact. But what we require is that each mi is a non-empty, and that's important, n-1 manifold with boundary, colored with the same set except you throw out process I.
But then if there is a intersection, you should care that the same vertex coloring the same color.
Oh, there's one coloring, and so each of these pieces inherits the coloring from M. So there's one global coloring, and which colors this, and it induces a coloring on the boundary where we can break this into pieces, where each of the pieces is colored by a subset.
Okay.
And each of the pieces has to be a non-empty manifold, n-1 manifold, which has a Ashburner coloring with these. Sorry, that should say Ashburner coloring. So the Ashburner coloring for an n-dimensional manifold is defined in terms of Ashburner coloring for n-1 dimensional manifolds, and then the base case is on the previous slide. Yeah, so that's a that should say Ashburner coloring. Okay, so that's what it means to be a Ashburner coloring for a manifold with boundary. There are other ways to define this that are much more succinct using subdivisions, but since we don't know what subdivisions are, we have to use this inductive proof. Okay, so this is a statement of the theorem. So we have a manifold, a complex. It has a boundary, a non-empty boundary. It says that there's an odd number of n simplexes that have all n+1 colors. So it's an obvious generalization of the picture that I showed you. So it's actually sometimes it's enough to take these classical theorems and use them as black boxes. But this one is actually a little bit instructive to go over the proof, because it's fairly straightforward. What time is it, by the way?
3:25.
Should we take a break? Okay, so let's take a 10-minute break, and then I'll